Hello, I'm Andrew Barron. I'm a professor of neuroscience at Macquarie University in Sydney. I focus particularly on comparative neuroscience. So I'm studying mostly insect brains, for me particularly the honeybee brain. Big question is, how does system structure influence intelligence? Now, in diverse intelligence, we want to compare different types of intelligence in different things. And at the start of this big picture lecture, I want to spend just a moment thinking about what that means, because I've often heard, and it often comes up, it's a legitimate question, that we can't compare intelligence until we can define intelligence. Now, personally, I don't think that's right. And to explain why, I want to give you just what's now a well-trod example by thinking about flight for a moment. Now, flight is something that we can all define. We can all agree that flight is moving through air under power. But what about comparing flight? So what if the question becomes, who's better at flight, a jumbo jet or a bumblebee? Now, to me, that question fails. I could argue that question from both sides and both answers would be right. To address that question of who's better at flight, we've got to be asking, well, what aspect of flight matters? And that depends on what's the reason for the comparison. So, and then if we deal with that, if we unpackage that, then the question works. So for example, if what matters to us, if the reason we're comparing is we want to know who creates more lift per unit of surface area, jumbo jet or bumblebee, well, we can easily make that comparison and we can get an answer that works. Now, I think that's how we can progress for intelligence. We can progress if we have reasons for comparisons that identify the aspects of intelligence that matter to us. So those aspects of intelligence could be who's fastest at learning, who's best at abstract reasoning, who's can rationalize a choice, who is the most strategic in their decision making, can give the best estimate of probability of events. All of these would be absolutely amazing questions. And we could move on all of these without having to define intelligence. And personally, I'm good with that. This gives me an awful lot that I can do. Now, why should the structure of a system influence the intelligence of a system? That's also worth thinking about for a moment. Well, all intelligence, all forms of intelligence manifest as a manipulation of information. And when I think about information, I think about Shannon information, information being something that reduces uncertainty, or just a bit more formally, information is the reduction of uncertainty about some situation associated with observing any variable that is causally correlated with that situation. Now, the structure of a system will influence how it can manipulate information, and that will constrain the kind of intelligence that it has. So for me, the big picture that drives my research, the big question that I'm trying to answer is if we can develop a really good understanding of how different types of structures constrain intelligence, then we'll be much further on in understanding different types of intelligence. Now, I want to talk for a minute, I shouldn't be doing this as a neuroscientist, but I want to talk for a minute about some examples from artificial intelligence. And these are really good examples because in AI, the structures of the systems that we're talking about are known in really intimate, absolute details. Now, complete disclaimer, I'm a neuroscientist, not a computer scientist. I'm not going to speak beyond my limits. And other teachers in the DI school, they're going to be far better placed to speak to this. But AI interests me because the examples they give are really, really clear. And there's this fascinating point of intersection and overlap with neuroscience. That's because the mainstay of artificial intelligence these days is an artificial neural network. Now, an artificial neural network has a very, 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 very loose biological inspiration at its core. In an artificial neural network, we have nodes, or they're sometimes called artificial neurons, connected into a network. And each node performs a reasonably simple learning rule that changes how they connect to the other nodes in the network. And this had at its original core a loose biological inspiration from Hebbian learning. Now, these artificial neural networks proved to be incredibly good at recognition and classification tasks. And if you build your network in layers, they become exceptionally good at classification and recognition. And then that gives us what's called in the literature a deep neural network, which has an input layer, which we feed information to, an output layer, which is the decision that the network has made, with these so-called hidden layers in between. And these have proven, even in the early days of AI, to be exceptionally good at handwrite recognition and face recognition tasks and other things like that. Now, the story of the development of AI has been mostly about changes, at least in the last decade, changes in the scale and structure of these networks, more than about changing the learning rules of the nodes in the network. Now, a really high-profile example is Alphago and Alphago Zero, which were developed by Google DeepMind. Alphago was developed in 2015, Alphago Zero in 2017. And I really recommend that you just take some time, just read about these, because it's really, really crazy fun stuff. Alphago was the first computer program that could beat a human grandmaster at the strategy game of Go. Now, this was thought to be computationally impossible because the strategy game of Go had so many possible permutations and moves that it was thought it was impossible to compute a solution. And it was thought that the only way a grandmaster could win at Go was through deep intuition and deep human intelligence. AlphaGo was the first to beat a grandmaster. To be fair, it did take the equivalent of 30 million hours of training, but AlphaGo did it. So AlphaGo was in 2015. AlphaGo Zero was the next Go playing computer program developed by Google DeepMind. AlphaGo Zero beat AlphaGo with 40 days of training. So AlphaGo Zero got better and it got faster. Now there's an ELO rating, which is a system for calculating relative skill levels in players of games in like chess and Go. And it's based on formal mathematics. And so we can say, as our point of comparison, that AlphaGo Zero has a higher ELO rating than AlphaGo. Now, there's quite a few important differences between these programs and how they work. But the difference that made a difference to the ELO rating of AlphaGo Zero versus AlphaGo was the structure of their neural networks. Now, I'm not going to get too technical, and that's because I can't. Because if you think I can give you a lecture about the mathematics of a Monte Carlo tree search, it's not going to happen. I'm a neuroscientist. But I want to give you an overview about what made the difference to these systems, because to me, this is what's really fascinating. These two programs basically used the same kind of system. What both of them had, is what we call a Monte Carlo tree search, which basically looks ahead and evaluates the probability of whether a move will be a winning move or not. And it looks through the tree of possible, expanding tree of possible moves the system could make. It's basically a predictive model for the outcome of any move that could be made. So both the systems have that. And that's combined with what the programmers call an intuition for whether a move is going to be good or not. Now, the intuition focuses the Monte Carlo tree search from exploring all possible moves into the region of the tree that the system intuits to be the best space for a likely winning move. And so progressively, by using this learned intuition to focus a tree search, progressively the program learns to get better and better and faster at playing a game like Go. And I absolutely love that we're in a space now where computer scientists are using terms like intuition to describe how their programs are working. I absolutely adore that. Now, the intuition in both AlphaGo Zero and AlphaGo came from a deep neural network, a very, very deep, very, very big neural network with over 40 hidden layers. That deep neural network was trained with the state of the Go board as the input. The outputs from the neural network was what it estimated as the best move and the likelihood of that move being a winning move. Now, if our comparison of intelligence is ELO ratings, then AlphaGo 0 is more intelligent than AlphaGo. But it's the structure of the deep neural network that made this difference. There's no difference in the learning rules they use. There's no difference in the Monte Carlo tree search that they implement. What makes the difference between these programs is a difference in how their deep neural networks are structured and how they're used. AlphaGo had what we call a convolutional neural network. It actually had two of them running in parallel, one of which evaluated which move a player would make. The other one evaluated the likelihood of that move being a winning move. AlphaGo 0 had a different structure to the network. It's formerly called a residual neural network. And it restructured the network, so rather than two, it had one network that learned simultaneously both the best move to make and the value of that move. The programmers called it a two-headed monster, which I think is a bit unfair. Now, this new structure in the system was better at playing Go, faster at estimating the best move, and more efficient in compute time. So these emerging stories from artificial intelligence give us fascinating, really resolved stories about how the structure of a system can influence the type of intelligence in that system. Now, what I would love to do in my lifetime is generate that same kind of understanding of the relationship between structure and intelligence for brains. Now, very quickly and very sincerely, brains are not computers. Brains are not deep neural networks. They fundamentally work in different ways. But even so, if we can get a better understanding of how information moves through brains as a system, then we'll do a better job at understanding the different kinds of intelligence that could be generated by those brains. And the system I'm working on most intensely is the insect brain, and most specifically, the honeybee brain. Now, I think of the insect brain as incredibly complex, but minute and really, really size constrained. And I think the insect brain's at this real sweet point where it's small enough so that we can actually comprehend it, but it's complex enough so that it's interesting to comprehend it. Insects amaze me with their intelligence, especially when you consider the compute power that's backing that up, especially the honeybee. A honeybee, I look at, what I see is a consummate learner. I see an economist that moment by moment solves these incredibly complex foraging economic choices. I see it as a consummate navigator. It's an optimizer of what and where it should forage in its environment. It's clearly capable of amazing learning in the lab. It solves complex classification problems. It can do even basic forms of abstraction. So for me, the question is understanding how the structure of the insect brain shapes that kind of intelligence. Now, what helps us and what helps me in analyzing the insect brain is we've had, well, the first images of the insect brain were from 1850 by Dujardin. And we're right now, and this is why I love being a scientist now, is we're right now having connectomes for insects emerging, full detailed resolves connectomes. So we're at the point where we really can ask meaningful questions about how the structure of the insect brain shapes its intelligence. The kind of approach I'm doing is to abstract the cognitive regions of the insect brain as networks, and then use computational modeling to explore the capacities of those networks and what the theoretic limits of those networks could be. So how does that kind of a brain constrain that type of intelligence? And I hope this will help us understand what makes a difference between an insect type of intelligence and a human type of intelligence. So for me, the big question is that we should expect structure to constrain intelligence. And if we can get a really good understanding of how different types of structures constrain intelligence, then we're going to be much further on in understanding different types of intelligence.